Pluto, once categorized as a distinct and legitimate planet in our solar system, was regarded as a unique object for many years. However, recent discussions led by famous astrophysicists Neil deGrasse Tyson and Michio Kaku have reignited the debate about Pluto's status, prompting further analysis of its role in the cosmos. These scientists have suggested that Pluto could potentially be on a collision course with Neptune, raising a wave of questions. How could such a massive event unfold? What would be the impact on the planets? And what are we seeing in the solar system as a whole, a rare and unique cosmic occurrence, or is there a more intricate and profound explanation behind this theory? Let's delve into what a possible Pluto-Neptune collision might imply. Once considered a smaller, more distant object in the solar system, Pluto still generates substantial interest among scientists. According to key studies from leading experts, Pluto's orbit is dangerously close to Neptune's, causing some astrophysicists, including Tyson and Kaku, to express concern about the possibility of a catastrophic impact between the two. The central question now is whether such an event poses a real threat to Earth. How could this happen in the first place? Pluto's orbit is one of the most unusual in our solar system. It takes an extraordinary 248 years to complete one full orbit around the Sun, meaning that since its discovery in 1930, Pluto has not yet completed a single orbit. However, its orbit isn't the only distinctive feature. It is also highly elongated compared to the more circular orbits of the larger planets. Additionally, Pluto's orbit is tilted by 17 degrees relative to the plane of the solar system, making it one of the most tilted orbits observed. This extreme tilt, combined with its elongated shape, adds complexity to Pluto's journey through space. A particularly fascinating aspect of Pluto's orbit is its interaction with Neptune's orbit. For around 2 decades during each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect in terms of planetary positioning. This raises an important question: why haven't Pluto and Neptune collided yet? The answer lies in the gravitational forces at play within the solar system. Immediately after Pluto's discovery, astronomers were puzzled by its orbit. Unlike the other planets, which follow relatively flat, aligned paths within the solar system, Pluto's orbit is tilted and elliptical, making it a subject of intense study. The fact that Pluto's orbit crosses Neptune's does not automatically result in a collision due to a gravitational interplay that stabilizes the two orbits. This balance, referred to as the three-body problem, demonstrates how Neptune and the Sun interact through their gravitational forces, predicting future positions based on their current motions. This phenomenon highlights how Pluto, Neptune, and the Sun's gravitational pulls ensure the two objects never collide. Astrophysicists note that this stable interaction is maintained by a mechanism called libration, which guarantees that when Pluto crosses Neptune's orbit, it does so at a point where Neptune is nowhere near. This ensures that the two bodies are never at the same point in their orbits at the same time. Additionally, Pluto's orbit exhibits libration, meaning it oscillates slightly around its path, further reducing the risk of collision. Another significant aspect of Pluto's orbital stability is the gravitational wobble effect, known as VZK wobbling, which explains how the gravitational pull from Pluto, Neptune, and the Sun influences each other, helping to maintain Pluto's orbit. Despite its apparent erratic course, the three-body problem and these gravitational forces are critical to understanding how planetary orbits evolve. These interactions not only shed light on Pluto but also enhance our knowledge of the broader workings of the solar system. Numerical simulations conducted in the 1980s revealed that while stabilizing forces help keep Pluto's orbit stable, slight changes in its initial conditions could cause its orbit to become more erratic over long periods. Despite these potential irregularities, Pluto's orbit has remained relatively consistent over millennia. Recent models have further highlighted how planets like Jupiter, Saturn, and Neptune help stabilize Pluto's path. For example, Neptune and Pluto follow a resonant orbit, meaning that for every 2 orbits Pluto completes, Neptune completes 3. This resonance is crucial to maintaining Pluto's orbital stability. However, Neptune is not the only planet influencing Pluto's orbit. Jupiter's gravitational influence also plays a significant role. Even Saturn has been shown to help stabilize Pluto's trajectory. These simulations suggest that Jupiter's gravity alone could maintain Pluto's orbit for billions of years, if not indefinitely. The cooperation of Neptune, Jupiter, and Saturn is thus essential for ensuring Pluto stays on its current course. Without these stabilizing forces, our solar system would be more chaotic, with bodies like Pluto potentially colliding with other celestial objects or being ejected from their orbits entirely. Studying such interactions not only helps us understand Pluto's orbit but also gives us valuable insights into the larger workings of the universe. Given this knowledge, Pluto's orbit becomes even more intriguing when considering theories of a potential collision with Neptune. The study of Pluto's complex orbit demonstrates the dynamic nature of how gravitational forces work in our solar system. It also reminds us that even orbits that appear chaotic can still achieve a balanced state through intricate interactions. The principle of orbital resonance plays a key role in this balance, explaining how Pluto's position and velocity, despite its irregular path, can still maintain stability over time. Programs simulating these orbital mechanics have provided valuable insights into how Pluto's orbit interacts with those of other celestial bodies, including Neptune. Small adjustments in a model's parameters can show how even slight changes in Pluto's position or speed could significantly alter its orbit. Despite stabilizing factors like libration, Pluto's orbital path can still be unpredictable. Variations in Pluto's initial conditions could lead to large shifts in its long-term trajectory. Nevertheless, despite its apparent unpredictability, Pluto's orbit has remained remarkably stable over billions of years, indicating an underlying order to its movement around the Sun, even when it seems chaotic. This unpredictability presents a challenge for astronomers, who must explain the evolving nature of planetary orbits. Although numerical simulations are invaluable for predicting celestial behavior, they also demonstrate the limitations of our models. These simulations are heavily reliant on the accuracy of their initial conditions, and even the smallest error can drastically change the results, making precise predictions difficult. Pluto's erratic orbit serves as a reminder of the constantly changing nature of the universe. While astronomers have made remarkable advancements in comprehending space, Pluto's unpredictable path shows how much more remains to be discovered. The study of gravitational effects from giant planets like Jupiter, Saturn, and Neptune provides scientists with important insights into the solar system's larger dynamic. Koku's research further highlights the unpredictability of long-term orbital mechanics. He suggests that even though Pluto's current trajectory appears stable, subtle changes over millions of years, caused by gravitational interactions with other planets, could eventually alter its path significantly. One of the key concerns raised by Koku is the potential for small, cumulative orbital shifts that, over time, could disrupt Pluto's stable resonance with Neptune. If this balance were to be disturbed, the likelihood of a close encounter, or even a collision, between the two celestial bodies could increase. While this scenario remains highly speculative, it underscores the importance of continually refining our understanding of planetary dynamics. To better assess such risks, scientists rely on advanced numerical simulations, which model the gravitational interactions between planets, moons, and other solar system objects. These simulations allow researchers to test different scenarios by adjusting variables such as orbital speed, inclination, and external gravitational influences. By doing so, they can predict how Pluto's orbit might evolve over millions or even billions of years. Despite the vast amount of data collected, planetary scientists emphasize that no simulation can provide absolute certainty. The chaotic nature of orbital mechanics means that even minor, unpredictable factors, such as the gravitational influence of an undiscovered object or the long-term effects of passing comets, could contribute to deviations in Pluto's orbit. The broader implications for the solar system. While the possibility of a Pluto-Neptune collision remains remote, the broader discussion has important implications for our understanding of the solar system's long-term stability. The study of Pluto's orbit serves as a case study in celestial mechanics, illustrating how gravitational forces shape the movements of planets and other objects over vast timescales. Moreover, these studies contribute to a greater understanding of planetary formation and evolution. By analyzing the gravitational interactions between Pluto, Neptune, and the other giant planets, scientists gain valuable insights into how the early solar system may have developed. Some researchers even speculate that similar gravitational interactions could explain the presence of other distant objects in the Kuiper belt, a region beyond Neptune that contains numerous icy bodies and dwarf planets. The discussion about Pluto's orbit also raises questions about potential threats to Earth from other celestial bodies. While Pluto itself poses no direct risk to our planet, studying its interactions with Neptune helps refine models that predict the movements of asteroids and comets that could, in theory, pose a danger to Earth. Public interest and ongoing research. Pluto has long captivated the public imagination, from its initial classification as the ninth planet to its controversial reclassification as a dwarf planet in 2006. The debate surrounding Pluto's status has not only engaged scientists but also sparked interest among the general public, fueling discussions about how we define planets and what criteria should be used for classification. Organizations such as NASA and the European Space Agency, ESA, continue to study Pluto using data from missions like New Horizons, which provided unprecedented images and scientific observations of the dwarf planet during its flyby in 2015. These findings have deepened our understanding of Pluto's surface composition, atmosphere, and geological activity, further emphasizing its importance in planetary science. Looking ahead, future space missions may provide even more detailed insights into Pluto's orbit and its interactions with other celestial bodies. Advances in space telescopes and deep space exploration technology could allow scientists to track subtle changes in Pluto's trajectory with greater accuracy, helping to refine long-term predictions. While the idea of a Pluto-Neptune collision remains largely theoretical, the ongoing study of planetary orbits highlights the dynamic and ever-evolving nature of our solar system. The complexities of celestial mechanics ensure that there is always more to learn, and as our observational tools improve, we may uncover new surprises about Pluto, Neptune, and beyond. In the end, whether classified as a planet or a dwarf planet, Pluto remains an essential piece of the cosmic puzzle, one that continues to challenge and expand our understanding of the universe. Objects in the distant solar system increase. To better understand the possibility of a Pluto-Neptune collision, scientists rely on advanced models and simulations that track the gravitational forces between these two bodies over time. These models take into account the complex interactions between Pluto and Neptune's orbits, as well as the influence of other planets like Jupiter and Saturn. This research is essential not just for understanding Pluto's future but also for refining our ability to predict the behavior of other objects in the solar system. Despite Neptune and Pluto currently maintaining a relatively stable relationship, uncertainty about the future of their orbits remains. The intricate balancing act that keeps the two planets on their present paths could change over vast periods of time. Even the smallest variation in their initial conditions could shift their orbits, potentially resulting in a collision or another event that disrupts this balance. This unpredictability underscores the limitations of our current knowledge and the challenges ahead in studying the long-term dynamics of the solar system. Understanding the forces that affect Pluto's orbit is just one part of a much larger puzzle. It provides valuable insight into the broader workings of our solar system. The interaction between Pluto and Neptune exemplifies the delicate balance needed to preserve planetary orbits, not just for these two objects but for the entire solar system. Studying Pluto's orbit is, therefore, vital for gaining a deeper understanding of the interactions between celestial bodies and how the solar system maintains equilibrium. As our exploration of space continues, studying Pluto and other distant objects becomes increasingly important. These objects, though far away, hold valuable clues that could help us understand the origins and future of our solar system. By examining Pluto's unusual orbit and its potential interactions with Neptune, scientists are learning more about the forces shaping our cosmic neighborhood. These discoveries may have broader implications for the study of other distant objects, including exoplanets and stars in remote galaxies. Ongoing research into Pluto and Neptune also serves as a reminder of the need for continuous learning in astrophysics. As scientists like Tyson and Koku have modified their perspectives in light of new findings, future scientists will need to remain flexible and open to new ideas. The universe is constantly changing, and our understanding of it must evolve as well. As technology advances and our exploration deepens, more surprises about planetary orbits and the forces governing them will likely emerge. In conclusion, the potential for a Pluto-Neptune collision remains an intriguing and complex topic that continues to engage scientists and the general public alike. The unique orbital features of Pluto, coupled with the complex gravitational interactions at play, make this a subject of great interest. While the stability of Pluto's orbit is reassuring for now, the possibility of future changes serves as a reminder of space's unpredictable nature. As we continue to explore Pluto, Neptune, and other solar system objects, we gain deeper insights into the workings of our cosmic neighborhood. This not only enhances our understanding of the past and present but also shapes our predictions for the future, helping us better comprehend the vast and dynamic universe we inhabit. The study of Pluto's relationship with Neptune offers crucial insights into the nature of the solar system. Comprehending the dynamics of their orbits helps astronomers refine models of how distant objects interact within the vast expanse of space. By continuously observing these interactions, scientists can not only predict potential future events but also better understand the forces that govern the movement of planets, moons, and smaller objects across the cosmos. These advancements in space exploration are not just about answering specific questions but also about developing broader theories that apply to a range of astronomical bodies. The research on Pluto and its orbit is an example of how focused studies on individual celestial objects can lead to significant discoveries about the universe as a whole. As our methods for observing space become more sophisticated, we may uncover even more complex behaviors in objects that we once thought were too distant or too small to be of interest. In addition to the scientific interest surrounding Pluto's orbit, ongoing debates about Pluto's classification highlight how our understanding of space is always evolving. As we gather more data and develop better technologies, what we know today may look completely different tomorrow. The journey to understanding Pluto's role in the solar system is a perfect illustration of this constant growth in astronomical knowledge. The idea of a potential collision between Pluto and Neptune also underscores the dynamic and interconnected nature of the solar system. Even though this event may seem far off or unlikely, the gravitational forces at play between planets demonstrate the complexity of their movements. Even the smallest force, such as a shift in the orbit of one planet, can set off a cascade of changes that ripple through the entire solar system. This interconnectedness is a reminder that space is not a static environment but a constantly changing and evolving system that can surprise us at every turn. Moreover, the fact that a collision between Pluto and Neptune could be prevented by subtle gravitational forces over billions of years speaks to the precision and balance inherent in the solar system. While many might think of space as chaotic and unpredictable, these phenomena demonstrate the existence of underlying order and stability governing the motion of planets. This knowledge has not only improved our comprehension of planetary orbits but also shown how these mechanisms have likely shaped the development of our solar system, and could continue to influence its future. As we venture deeper into the study of Pluto and Neptune, ongoing discoveries will undoubtedly push the boundaries of our understanding. Scientists continue to refine their models and conduct simulations to predict how far-off objects will behave, helping to uncover the deeper workings of the universe. Each new finding, regardless of how insignificant it may seem, contributes to a broader perspective on the forces that govern our solar system and beyond. In essence, the potential for a Pluto-Neptune collision, though remote, serves as a captivating reminder of the incredible complexity of our solar system. It is a testament to the ongoing quest for knowledge and a reflection of how scientific understanding constantly evolves with new observations. While our grasp of these distant planets and their interactions may never be entirely complete, each discovery brings us closer to finding answers to space's mysteries, paving the way for future generations to explore even deeper corners of the cosmos.